Question is, can we do better than n log n? Well, the answer is yes. However, we have to partition the problem differently. Let's go to the optimal solution directly. We can view each optimal solution as a sequence of choices. Okay, so for example, there is a choice, the maximum subarray contains an or not. Of course, the optimal solution may contain an, so the answer is yes. It may not contain an, so the answer may be no as well. Depending on the answer, we actually can split the problem into one or more subproblems. Okay, so let's look at this more carefully. How about the first case? The optimal solution indeed contains the element a sub n. So in this example, minus 1, that's my an, so the optimal solution contains this minus 1. Then the problem becomes an easier one. We call it max ending. That means you want to find the maximum subarray that actually ends at this element. And we know from our previous discussion, this can be done in linear time. Okay? The other case, the optimal solution does not contain this minus 1 element. If that's the case, then we can safely ignore this element, right? And the optimal solution to the original problem is exactly the same as the solution to this smaller problem. Find the maximum subarray from the array A from 1 to n minus 1. We use this max sub I to denote the maximum sum in array A from 1 to I. We can generalize the observation we just made. So maximum sum sub I equals two possibility or two cases. Either it's the one that ends at the element a sub I, or maximum sum I minus 1. This is the recurrence we establish for the value, the optimal value of max sub I. And the original problem, the solution to the original problem is in max sub n. So now let's use example with this input to see how we use this recurrence to calculate maximum sub n. Okay? So here is the input instance. Now let's calculate maximum ending first. Okay? First element, by definition, maximum ending P equals AP. It's the first element itself. From the second element, you actually have two options. One is to extend the already calculated maximum subarray that ends at a sub I minus 1 with this element, new element a sub I. That's one option. The other option is just let a sub I be a subarray by itself. You compare the value of these two options and you take the maximum value of them. Okay? So for example, the first element, the maximum ending, is itself, so it's minus 2. And for the second element here, the element itself is 5. And the other option, extending the previous subarray, gives you minus 2 plus 5 gives you a value of 3. Because 3 is less than 5, so you take 5. So 5 is your answer. Okay? And then for the third element by itself is minus 2. The other option, extending the previous subarray, you get 5 plus minus 2, that's 3. So 3 is larger than minus 2, and 3 is the answer. So you can do that for the entire array. And now we have calculated all the values for maximum ending. And then we can calculate the maximum sum using the recurrence we just seen before. Okay? Again, for the first element, by definition, The maximum sum is the element itself, so it's -2. So it's -2. And from the second element, we use this recurrence to calculate max sub I. Okay, there are two cases as we mentioned. It can be max ending I or max sub I minus 1. Okay, so let's see from the second element one by one. Now let's look at the second element. The second element has two options. First option, it takes max ending 2, the value is 5, or it takes max sub I minus 1, the value is -2. 5 is greater than -2, so you take 5 as the value for max sub 2. I equals 3. You have again two options. You can choose from max ending 3 and max sub 2. Okay, so you pick the larger one from 3 and 5. 5 is the larger one. Okay, and then for I equals 4, you pick from 10 and 5, and 10 is the bigger one. At the end, we have this 10 as the optimal value. That's the maximum sum. And we know 10 comes from here, and it corresponds to this subarray, 5 minus 2 and 7. Okay? This idea is dynamic programming idea. Okay? It's different from the divide and conquer paradigm in two ways. One, we don't partition the problem into two even-sized subproblems. We actually think about the optimal solution as a sequence of choices. Okay, we make a choice and then we see what is the remaining subproblem. The second difference is we need to set up a recurrence, something like this. We need to set up a recurrence to calculate the optimal value. Okay? For this dynamic programming solution, there are two for loops, and we know both of them are theta n procedures, so it's linear to the size of the input. So this dynamic programming approach is more efficient than the divide and conquer algorithm we just developed. So in summary, we developed a linear time dynamic programming algorithm, and this dynamic programming algorithm partitioned the problem differently than the divide and conquer algorithm, and also use a recurrence to calculate the optimal value.